So now I'd like to discuss potential sweep methods and how potential sweep methods can be used to learn more information about electrochemical systems. So start with an overview. For example, we'll start by talking about linear sweep voltammetry, which is where we might have some potential. And as a function of time, we may linearly change the potential. And of course, we'll measure the current response from EI to EF as we sweep that potential. And what we'll see is this often results in a peak current. And we can identify things like standard potential from this type of analysis. And then in the end, we'll also want to understand how these two are related to concentration of O as a function of position and time, and concentration of, for example, R. So if we're driving a reaction, O plus an electron going to R, we drive O plus an electron going to R, O will get depleted, the surface, R will get generated at the surface, and these curves will be dependent on the potential, the time, and actually the scan rate, volts per second. And we're going to see how that all works out. And then what we'll follow with is a discussion of cyclic voltammetry. This is very similar, except in this case, we're going to go from a starting potential, we're going to ramp up to a reversal potential, and go back down to the starting potential at some scan rate in volts per second. We're going to traverse this potential window. And the current response often looks like this classic so-called duck shape. And we will understand why that duck shape is found and why you can identify E naught prime as the average between these two peak potentials. So we'll start now exploring linear sweep voltammetry in more detail, where we're going to sweep the potential, and we'll think about how we set up solving the diffusion problem, but like in the previous potential step experiments, we won't actually solve the diffusion problem because it needs to be solved using numerical methods. So we're going to define E of the electron as a function of T equals some initial electropotential times the scan rate times time. So this again is scan rate in volts per second or millivolts per second. In this case, in the simplest case, we're going to assume a Nernstian response. So again, what does Nernstian mean? So the Nernst equation. The Nernst equation describes what about electrochemical systems? The Nernst equation describes the thermodynamics of electrochemical systems. And if you have a Nernstian response, it means the kinetics are very fast relative to the current that's being passed. So Nernst equation applies always at electrode surface. Okay? So we're going to assume that. Now, we can define some initial conditions similarly to we did before. CO of x and t. So we're going to assume O plus n electrons goes to R. That's the reaction we're interested in. C0 x of t. I should say x of 0, okay? So the concentration of O for all x at time equals 0 is just equal to CO star, like before. And now we're going to have to also define a boundary condition at electrode, right? So at the electrode, we know it's Nernstian. The electron transfer kinetics are very fast. So what kind of boundary condition can we define? Well, we know the Nernst equation holds. Right? So if the Nernst equation holds at the electrode surface at x equals 0 at all times, this effectively tells me what the ratios of my concentrations must be for any given electrode potential. So as I sweep the electrode potentials, I'm actually changing my boundary condition. So this is what makes solving the differential equations very hard, or why you do it numerically, is that the boundary condition now has a time dependence. But I can rearrange this equation and write CO 0T over CR 0T. So the concentration ratio at the surface as some function of T, and that's going to be equal to the exponent of NF over R T EI minus BT minus E naught prime. Okay, so there is the Nernst equation. That's an R. And so this time dependence boundary condition, you can't just simply use the Laplace transform to solve it, so it needs to be done numerically, which we won't do now. Well, we can't do. We have to do it on a computer, but you could do it in a software package. You could find a solution to this. You can simulate this in programs like COMSOL very easily. But we can write the result, the general working curve that shows what the result of the experiment is. And so this is a figure in Barton-Falkner, is a plot of the normalized potential relative to E1 half. And this is the normalized current, I over NFA CO star DO, the 1/2, and F over RT to the 1/2, scan rate to the 1/2, okay. On this axis, if this is plus 100 millivolts, or in Barton-Falkner, negative 100 millivolts, and this is plus 100 millivolts versus E1 half. The curve, this is 0.1, this is 0.4. The curve starts low, so if you're very positive, right, we're looking at O plus N electrons going to R. We're sweeping negative, we're starting out with all O, so if we're very positive of the half-wave potential, or the standard potential for this reaction, we're not going to pass really any current. And then as we start to approach the half potential, we start to see current, and then we come to a peak, and then we come back down. And this is the general curve, and we can define some parameters from this curve, and we'll see why this is important in a second. So E1 half is right here. And if you remember from chapter 1, E1 half is defined as E naught plus RT over NF times the natural log of the ratio of the diffusion coefficients. So if the diffusion coefficients are roughly similar, E naught is the standard potential. We can define a peak potential, EP, a negative, this is a cathodic, EP cathodic, so sweeping negative, it's cathodic peak potential. And I can define a cathodic peak current also. and I can derive from the numerical solution formulas for these various parameters. So we'll look at that. So IP, peak current, is equal to 0.446 F cubed over RT to the 1/2 n to the 3/2 A dO to the 1/2 CO star V to the 1/2. Okay. And these, of course, are the parameters we can control. This is, again, the scan rate. This is the bulk concentration. This is the diffusion coefficient. And the area of the electrode. And we can find the peak potential. This is a Nernstian system, remember? This is Nernstian, which means the kinetics are fast. We can find the peak potential. And that's equal to E 1/2 minus 1.11 RT over NF, or, well, this term is about 28.5 millivolts over N. Okay? So basically what it's saying is this distance here is around 28 millivolts. We'll say 29 millivolts. Round up. And we can also define something called the half peak potential, which is a little bit easier to measure sometimes. Here's EP over 2, so that's where the current is half the peak current. And EP over 2 equals E 1/2 plus 1.09 RT over NF. So E 1/2 is sort of halfway between the peak and the half peak potential. Okay, so we can use this to analyze voltammograms if you know the behavior is Nernstian. And this is for a linear sweep, right? And so in this case, we just swept the potential in one direction. And now what we want to do is we want to look at this. And I don't expect you guys to memorize these equations. If you need to use them, you can look them up. But you should sort of know what they depend on. So let's actually look at that. So you can see here the peak current. What does the peak current depend on? Well, it depends on the area of the electrode. That makes sense. Depends on the diffusion coefficient because it's a diffusive process, right? And it depends on the diffusion coefficient to the 1/2, right? And that kind of makes sense because as things diffuse faster, you can collect species from a further distance and get larger currents. It's linearly dependent on the concentration of species. That makes sense because that's going to set how much material is in the electrolyte nearby that you can extract and reduce to R. And it depends on the scan rate. So why would it depend on the scan rate? Well, if you think about it, current is dq dt. So it's how much charge is passed per unit time. And if I scan very fast, I'm going to, in this case, reduce all the O that's within a diffusion length of my electrode very fast. And if I scan faster, I get more current because I'm, in this case, reducing the same amount of material under a shorter time period. But it doesn't scale linearly with scan rate. It scales with the 1/2, and that's because as you scan faster, you can access less of the material as a function of distance away from your electrode surface because you don't have as much time for species to diffuse the electrode surface. Okay, we'll investigate this and think about this in the laboratory, in the simulation. You'll get very familiar with how to think about time and scan rate and current response. So let's go now to cyclic voltammetry. Cyclic voltammetry is very similar, except we're going to do a potential reverse step. So let's do CV, right, CV. And now I'm simply going to scan the potential one direction and then reverse back. And we define this as E lambda, EI, and this is time. And this is, we'll call this lambda, time equals lambda. So we can define for 0 to t smaller than or equal to lambda, E equals EI minus scan rate times the time. So this is this line, right? It's that first line. And then for t, it's in blue here, right? For t greater than lambda, E equals EI minus 2 VT plus VT. V lambda, sorry, of course. And that's just the equation for this line. Okay. So we can define these equations, which describe how the potential changes with time. And then we can use that to solve the diffusion equation numerically and get the response of our electrode system as we sweep the potential forward and back. One thing we want to think about, though, is what other responses might we measure while we're sweeping potential? So this is for Faradaic. This is going to be a Faradaic response. What other types of currents can we measure? Well, we learned in chapter 1 that we have non-Faradaic currents. What are non-Faradaic currents due to? Due to charging of a capacitor that forms the double layer. So qualitatively, if I measure E curve, I'm going to sweep the potential and look at the response. If I have no redox species around, I'm going to get this nice capacitive curve, which you guys have measured. And this is purely non-Faradaic. Non-Faradaic. And then if I add a redox couple, and say I'm scanning very fast, because the capacitive current goes as CD times the scan rate. And remember from before, the peak current on my voltammetry is proportional to the scan rate to the 1/2. So if I scan very fast, this capacitive current grows much faster than the peak current for my Faradaic reaction. And that's because for the capacitive current, nothing has to diffuse. You're just charging the capacitor right at the interface. And we assume that the ions in the electrolyte can move very fast. However, for the Faradaic reaction, we actually have to diffuse things from further away from the electrode surface. And so that's what gives rise to this 1/2 dependence on the scan rate. And so if you scan fast, you might have a very large capacitive background. And then if you scan very slow, this is fast, slow, what do we expect to happen when we scan very slow? Well, if we scan slow, this current will go down much faster than this current. So we'll be able to better resolve our peaks. And so that's something to keep in mind as you change scan rate, the different dependence on non-Faradaic capacitive current, or as we'll learn later, the current due to a surface-absorbed redox species also scales linearly with scan rate versus a freely diffusing redox species, which scales as to the 1/2 power. Okay, so what can we learn from a voltammetry experiment? Well, based on our analysis of the linear sweep voltammetry, we know how to define some parameters. So let's just do a qualitative assessment, and I encourage you to do the reading. Do the reading from Jillian Dempsey's group in JChem Ed, which gives a nice introductory description of voltammetry, very qualitative level, which is really useful to reinforce what we're talking about here. So if you have a Nernstian system, what we get on the forward sweep, I'm going to plot this as E versus E 1/2. On the forward sweep, get a peak. And then on the reverse sweep, I'm going to get a peak too. And so this is interesting. So I can basically study now the O plus electron, N electrons, I should say, going to R on the forward sweep. I use the Texas convention. And on the reverse sweep, R going to O plus N electrons. So I can look at the forward reaction and its kinetics and mass transfer. And then I've generated some species here. So on the forward sweep, I generate R. On the reverse sweep, you consume R. So this is nice. For example, imagine R was not particularly stable and difficult to put in a bottle. You could study the properties, the electrochemical properties of R in situ in your electrochemical cell, where you generate that R immediately before studying it. And so that's interesting. We can define some numbers here. So there's I, P, and I, P anodic. So in the Bard and Faulkner notation, define E, P cathodic, E, P anodic. Of course, this is E1. E1 half is 0 here, right? And we know from our previous analysis that the distance between E1 half and the peak potential is 28.5 millivolts over N. And it's the same on the reverse scan as well, approximately. Of course, it depends a little bit, right? How far you scan. So if you only scan to here, your curve's going to look a little different versus if you scan way out here. But these numbers are pretty close. And the nice thing is you can use modern software, which you will do in the project, to simulate under a variety of conditions what sort of response you get. And so what's nice is we can estimate now E1 half, right? E1 half, approximately formal potential. And this is just going to be EPC minus EPA over 2. It's the average of those two peaks. And one thing we'll talk a little bit more about later, and you will explore also in the simulation, is if I make the kinetics slow, what happens is these peaks shift apart. And so you start seeing ducts where this distance is delta E P much greater than 58 millivolts, right? Which is what it is here, or 57 millivolts. Much, much greater than that. But still, as long as the peaks are symmetrically split, if the forward and reverse kinetics change in the same way, I can still estimate E naught prime from the average of these two peaks. And so that's what many people do in voltammetry. And it works because we have solved the diffusion equations to determine what those parameters are. Okay, so now what I'd like to do is I'd like to think a little bit about what the concentration gradients look like that develop during voltammetry. And this, by the way, would be an excellent question for the final exam. So here's my voltammogram. And let's think about what would happen as we progress through this voltammogram. E1 half, which is approximately E naught, right? And then let's look at the peak potentials. So let's call that A, B, C, D, E, F, right? And now could we go and figure out what the concentration profile should look like under these conditions? Well, let's think through this. So at A, let's actually do like, let's call this X. So let's do X first, right, when we're starting. And at X, well, we haven't done anything yet. The current's almost 0. we start out with all O plus n electrons going to R, so all O. So we should basically have CO star everywhere, and CR star equals 0 everywhere, right? Concentration function of x. As we start to approach E naught, we start to pass current as O near the electrode is reduced to R. And if this is Nernstian, what should my concentration gradient look like as the potential reaches E naught? So if the Nernst equation governs what I find at the electrode surface, at E naught, I better have equal concentrations of O and R. And the gradient here determines the current, the flux. The flux of species, flux of O to the electrode surface, determines the rate of this reaction, determines the current I measure. Now, at the peak potential, what happens? Well, at the peak potential, what we've done is we have maximized the gradient in O. So if you remember from our previous studies on the stirred system, this is unstirred, remember? We're still doing unstirred voltammetry. So this is purely diffusion controlled, no convection. If we think about the concentration profiles, and we want to maximize the gradient in concentration to maximize the flux, because that's what happens at the peak current, what do we want to do? How do we do that? Well, the surface concentration is pretty close to 0 of O, right? And we go into the bulk. Now before we had a fixed diffusion layer boundary, but here the diffusion layer boundary is changing with time, right, as species are diffusing from further and further away in the electrolyte. So the peak current happens when you have depleted enough O to set the surface concentration close to 0, but you haven't waited very long, because if you wait too long, then you'll start pulling species from further and further out into the electrolyte, and this curve will have a slope that is decreasing. So it's sort of a convolution of the time of diffusion versus the surface concentration set by the Nernst equation that determines where that peak current occurs. Okay, so that's the maximum slope, right? We better have something that looks similar in R as in O. Now if we wait a long time, we keep sweeping, are these boundary conditions really going to change that much? No. We can't lower the concentration of O at the electrode surface much more. But what we can do, right, we can pull O from further and further out of the electrolyte. And so what that means is the slope, right, the flux goes down as we sweep further and further. And that's exactly what's going on here. And in fact, this goes down by t to the negative 1/2, just like in the Cottrell equation. Because you're not really changing the boundary condition here, even though you're sweeping the potential. Why the current's changing is simply because the concentration profiles are changing as you consume O and generate R. Okay, so this is sort of, this part maps actually on very nicely onto what the Cottrell equation predicts. So then what happens when I sweep back? Well, I've generated all this R now in the vicinity of the electrode surface, and if I sweep back, thermodynamics based on the Nernst equation is going to say we don't want all that R at the electrode surface. We want to convert it back to O. And so this R will start to convert back to O. And what you'll see is you actually get a hump here where the concentrations, you've started to deplete the R and generate more O, but that hasn't yet affected the area far away from the electrode because the time for diffusion hasn't been long enough. And so you see these interesting concentration profiles. So you can CO, CR. Okay? Get these interesting concentration profiles on your reverse sweep. And then at the peak current, the same sort of thing is going on, except we have now the maximum slope here of O and R. So the current, this is the max or peak current, I, P, A. And then at time F, these humps start to go away as the current goes back to 0. These humps start to go away as you go back to your sort of steady state or your initial condition. And that's why you have all this hysteresis in this curve, right? The forward sweep doesn't trace the backward sweep because the concentration profiles are a function of time, not only a function of potential. So what I encourage you to do is to look at all these concentration profiles, make sure you understand them, and explore the peak shapes that you get via simulations to interpret some of the experimental data you collect in the laboratory. Okay, and the last thing I'll mention, and you'll do this in the project, you'll measure the voltammetry of methylbiologen, which has 2 redox waves that follow each other at different potentials. And many molecules are like this. So you might have O1 plus an electron goes to R. O2 plus an electron goes to R. This is actually, I guess, 2 different redox species, but the same sort of thing happens when you have a single molecule that can undergo 2 redox transitions. The diffusion profiles are a little different. But anyways, you can plot these things and you can actually see a series of peaks here. And you'll notice the second peak is higher than the first peak. And that's because we have this reaction occurring here, and then it's Cottrellian decay to a background current of this reaction, and you have a linear addition of the second reaction kicking in at the second E naught. So this is E naught 1, E naught 2. And you can explore that also in the simulations by adding different redox reactions, adding molecules with multiple redox reactions, and I encourage you to play around with that to make sure you understand all this. So thank you for your attention, and that concludes this portion on potential sweep methods.